Now we've been checking out some plates and spherical objects, point charges to try to figure out their electric fields. Well, those are just some shapes. Wouldn't it be nice to be able to do every shape? Well, using our friends, the techniques that we learned from our math department, can we use some calculus perhaps to find things that are a little bit different? Stop signs, long, thin lines, for example. Well, absolutely we can. So let's figure out a couple things. Let's use some of those lessons that we learned from the math department to figure out actually where we at. All right, now what I'd like to do is figure out, we're going to have a long, thin rod. And I'm going to make a little squiggly line at the end because this rod is not going to be just any length, but it's actually going to be infinitely long. So I'd like to know, what is the strength of the electric field at point P? So the electric field at some arbitrary point, point P, is the question. And the electric field is created by this rod. Now the rod itself is positively charged. It really doesn't matter to us whether it's positive or negative or whatever, but it just changes the direction of the field. I'm more interested in the magnitude of the field. Now to make our life a little bit easier, I put point P right along the x-axis so we don't have a lot of forces and fields being developed off on angles in the y direction, so everything kind of is focused in this direction. So our question is, what is the strength of that electric field? All right, now we need a little bit of framework of sorts, so let's set up some values here. So let's say the distance from point P over to the end of the bar is r, some radius. So how far away is point P from the front end of the bar? Answer is r. All right, if we look here, I'm going to take this bar and I'd like to divide it into little pieces. So let's take a look and see where this electric field is coming from. Is the front of the bar, that first little sliver of bar, creating some electric field at point P? Absolutely. And is there some piece of the bar back here helping create electric field at point P? Sure. Is there a little piece back here creating some electric field? And voila, all the way down the line of this bar, aren't those pieces creating some electric field at point P? So I'm going to break the bar into little pieces. And these little pieces have size to them, and we're going to call that dx. So each little sliver is a little bit of the bar dx. So we're going to break that bar into a whole bunch of different things. And if we look here, we'll have some length to the bar. We'll say this is 0, and then it has some length L. Now, in this case, the bar is, L is actually going to be infinitely long. All right, now, our job is this. Take the bar, break it down into little infinitely small pieces. Then, once I find the formula for those little pieces, can I take those and start to add them up and then use integration to figure that out? So let's look at the root of it all. All right, we know that E is equal to 1 over 4 pi epsilon naught Q2 divided by R squared. That's our base formula for most things. So if I take a look here, I'm not really concerned about this particular formula. What I'd like to do is figure out how much strength came from each little sliver. So we've got some dx's here. So the trick is this. I'm going to take density, the density of the bar itself. All right, now when I talk about density, we're not talking about mass density, mass divided by volume, mass divided by area, mass divided by length. Those are the things that we're actually accustomed to using, whether we're talking about gravity or something in the land of gravity land. All right, now, what we're talking about now is charge density. The density of the charge per volume. The density of the charge per area. The density of the charge per unit length. So when I determine what the density is here, what I really want to do is find the density of that, the density of the charges per, in this case, because it's a long, thin rod, per the length of it. So instead of taking mass, we're going to divide by Q, sum total charge of this, and divided by some length of the bar. All right, now, when I'm looking at this particular formula and all of these Q's, I see no mention of dx's in here or lengths or anything like that. So density is the magic link between charge and actually the length of the bar. So if I look here, I can take the density, and instead of taking an entire Q, can I take a little bit of charge? So as I look here, a little bit of charge comes from a little bit of sliver of the bar. So this distance here, this little sliver, is not just any length, but it's dx in length. So let's just take a look at that little sliver dx. Yeah, it's really tiny. How much charge does it have? Ooh, it has dx, dx has dq of charge. So when I look at density, we could take the total charge of the bar divided by its total length, or can we take, since density never changes, a little sliver of the bar and divide it by a little sliver of the length. All right, now when I take a look at this, I can solve this for dq, and then I have rho dx like this. Now, in our formula here, what I'm interested in is not E, but what little change or what E came from that little sliver. So what I developed from this little sliver of dq is a little bit of electric field. How much electric field? dq is the amount of charge, dE is the amount of electric field created by that little bit of dq. So when I write my formula out, I have 1 over 4 pi epsilon naught. And instead of saying Q2, what I really have here is the charge that was created by dq. All right, now when I look at the distance here, how far is it from point P to dq? So we're going to actually measure from here. Isn't that going to change depending upon where I am on the bar? So from point P to the front end of the bar, we're going to call R. And the distance from 0, the front end of the bar, to wherever our dx is, I'm going to call x. So how far is it total to get to this little bit of dq charge? It's going to be r plus x. So we have r plus x like this, and then we're going to have to square that because that's our new radius. So now we have a nice little formula at this point in time to figure out how much electric field was created by that little bit of dq.